Greetings, AP Chemistry. This is the very last required podcast out of the break watching. This is podcast 13.3. We're going to be talking today about the properties of solids and the three different kinds of solids. Later on this week, I'm going to post another optional one. You don't have to watch, but it's going to consist of solutions to some of the problems I asked you guys to do here in these assignments. So if there is something you would like to see done, post it to the Facebook group or email me, and then I can take a look at those and podcast some of the answers to your questions here later on this week, probably like Thursday or Friday. Be advised that we will have a quiz on all this material when we come back to school. So, today we're talking about solids, and there's two general classes of solids that you guys should know. One is, if we break all solids down into two categories, you can classify them either as amorphous, meaning they have no regular arrangement of the particles that make them up. Okay, so I won't write that all down. You guys can do that at home. But an example of this would be glass. Okay, if we were to use our magical chemistry glasses and look at glass down on a molecular level, you would see that there are not any regular arrangement of the particles in glass. And glass, by the way, guys, is made out of silicon dioxide. Okay, so the particles do not have a regular arrangement. Crystalline solids, on the other hand, which is what we're going to focus on today, do have a regular arrangement. Okay, that is what defines a crystalline solid. They have a regular arrangement of the particles that make them up. And the particles could be atoms, they could be ions, they could be molecules, or they could be, well, that's pretty much it. But that's the definition of a crystalline solid. It has a regular arrangement of the particles that make it up. Now remember, we've referred before, guys, to a crystal lattice. Okay, that is the three-dimensional structure. It's a repeating arrangement of those particles in three dimensions. Okay, so we're going to focus mostly on these because they're more interesting. Before we go in and we talk about crystalline solids, though, we're going to consider a question. And here's the question right here. I have these four different crystalline solids. We have crystalline water solid, which is also known as ice. We have gold, sodium chloride, and diamond. These are all examples of crystalline solids. What I would like you guys to do is, using the melting point information over here, I want you to pause the podcast here really quick and determine, and rank these rather, from weakest intermolecular forces of attraction to strongest. I should maybe say interparticle attractions, because if we look at the smallest unit of sodium chloride, it's not a molecule, it would be separate ions, sodium and chloride ions. So rank these substances in order of increasing interparticle attraction. Okay, pause it real quick. Okay, we're back. Now, the way you would go about doing this is, of course, we said before that melting points, boiling points, vapor pressure, all these things depend on the strength of the intermolecular forces of attraction that are holding the particles together. Well, if we compare the melting points, okay, water has got the lowest melting point, followed by sodium chloride, followed by gold, followed by diamond. So you would expect that the magnitude of the intermolecular forces or interparticle forces of attraction acting between particles in these solids would follow that same order. So water will have the weakest intermolecular force of attraction. This is weaker than sodium chloride, which is our next one, which is weaker than gold, which is weaker than carbon in the form of diamond. Okay, because these melting points are really a proxy for the strength of intermolecular forces of attraction. So there we go. Now, these actually turns out these are all examples of the four different classes of crystalline solids. And what differentiates these different substances and gives them different particles are the types of forces that are holding the particles in the crystal lattice together. So here we go. Let's take a look at that really fast. The four classes are these. We have things we call molecular solids. These are solids that are formed from molecules. So the individual particles in the crystal lattice are discrete, separate molecules. Okay. Now, if we think about the forces that can act between molecules, they can hold these together in the solid state. We said what these are before. We can have dipole-dipole attraction, okay, that hold these together, the separate molecules together. We can have dispersion forces, and we have hydrogen bonding. These are the three possible intermolecular forces of attraction that can hold molecular solids together. Now, if we look at these forces, these are relatively, compared to chemical bonds, these are relatively weak. And so because the interparticle attraction in a molecular solid is relatively weak, these tend to have low melting points, okay, and they're usually soft and easy to break, okay? That is due to the type of force holding the individual particles together to each other. The next class would be covalent network solids, okay? The individual particles in a covalent network solid are atoms, okay? And a good example of a network solid is diamond, okay? Diamond is just straight up carbon. The individual particles in the crystal lattice are carbon atoms. And what holds these carbon atoms together and what attracts them to each other are covalent bonds. Okay, that's why it's called a network solid. The particles in the solids are held together by covalent bonds. Okay, now we know that covalent bonds are really strong, and so what that means is that these usually have extremely high melting points because it takes a lot of energy to overcome the interparticle attractions holding the solid together. Also, they tend to have poor electrical conductivity as a consequence of their bonding, but not always. We're going to look at examples of ones that don't. And they tend to be pretty hard, okay, because the bonding is strong. Next class would be ionic solids. In an ionic solid, the individual particles at the points of the crystal lattice are ions, okay? As we know, these are held together by ionic bonding, which is very strong. Because ionic bonding is strong, the force holding the ions together is strong. These tend to have really high melting points, okay, because there's strong attraction between the ions in the solid, and they tend to have, in the solid state, poor electrical conductivity. Of course, we know that if we melt them or if we dissolve them in water, they will conduct electricity. The last class are metallic solids. In a metallic solid, the individual particles, of course, are metal atoms, and these are attracted to each other via metallic bonding. We're going to talk about what metallic bonding is today and review that from last year, but because metallic bonding is very strong, these tend to have high melting points, okay, and by virtue of the nature of metallic bonding, they have good electrical conductivity, and they tend to be malleable and ductile. We'll talk about what that is here in a second. So these are the different types of molecular solids, and the distinction between them is what are the smallest particle of the solid, and what kind of force are holding them together to each other. Oh, excuse me. Okay, so let's look at each of these classes individually. The first type we're going to are the molecular solids, okay, which are formed from individual molecules. And like we said before, the type of attraction that are acting between molecules can be either dipole-dipole attraction, hydrogen bonding, or dispersion forces. Now, these attractive forces are relatively weak, okay? So let's look at an example. This picture down here is a picture of ice, okay, of crystalline ice. Now, this is a crystalline solid because if we look at the arrangement of the individual H2O molecules here in the crystal, there's a regular arrangement of these molecules in space, okay? If I was going to identify the force that is holding these, or that is attracting these water molecules to each other, that would be good old hydrogen bonding, okay, of course. And so if we just look at this crystal lattice, it's a repeating pattern of water molecules held together in a regular arrangement. Now, because they're held together by hydrogen bonding, and because hydrogen bonding is a relatively weak attractive force, you would expect that compared to other types of solids, molecular solids will have low melting points because it does not take, comparatively speaking, guys, everything is relative. Because the intermolecular forces attracting water molecules together are relatively weak, that leads to a low melting point because it does not take, comparatively speaking, a lot of energy to overcome the attractive forces within this solid, okay? So any solid where the individual particles are molecules, that's a molecular solid, and they're held together by weak intermolecular forces of attraction. Okay, that is what defines a molecular solid. Now, these do not conduct electricity, okay, because there are no mobile electrons, okay? If we look, the electrons that are here in this molecule, or in the solid, we have electrons that are localized in the chemical, and then we have electrons here, the lone pairs of electrons on each of the water molecules, but they're not really free to flow through the surface of the crystal, which is why that has poor electrical conductivity. Okay, so that is what a molecular solid is. The next class are network solids. Okay, network solids are formed from atoms. Okay, these are held together by covalent bonds. So, what do we call a group of atoms held together by covalent bonds? The answer to that question would normally be a molecule. So, a network solid, which is a network of atoms held together by covalent bonds, really is like one big molecule. Okay, it's basically what they are. Because covalent bonds, which attract the atoms to each other, are relatively strong, okay, network solids tend to be pretty hard, and they tend to have very high melting points because the attractive force acting between the particles in the crystal is very, very, very strong. Okay. Examples. The classic examples of network solids are all allotropes of carbon. Okay, allotropes meaning, if you see this word allotropes, that means different forms. Okay, different forms of the elements. So, graphite or carbon rather can exist in several different forms in the pure, just as pure carbon. One is diamond, another is graphite, and of course somebody's going to say, you know, well, can't it also be Buckminster fullerene? And the answer to that question is yes. These are the different allotropes of carbon. Okay, and the difference between these different network solids is the type of bonding that they participate in. Okay, so we're going to consider these two examples, diamond and graphite. These are both network solids, and the reason they're network solids is because they consist of atoms that are bonded together. Okay, now if we look at diamond first, okay, diamond is shown right here. Okay, what distinguishes diamond from graphite is the way that the atoms are bonded together. If you look at each of these carbon atoms in graphite, and I ask you, what is the geometry about each of these carbon atoms, you're going to tell me, well, of course, Mr. Harper, those are tetrahedral. Okay, and if we look, therefore, at the hybridization that has to be on each of the carbon atoms, we know that each of the carbon atoms has to be sp3 hybridized based upon that geometry. Okay. Now, because of the way these are bonded together, okay, so if each of these carbon atoms is attached to each other through a covalent bond, you can imagine that it is going to take a lot of energy to break these covalent bonds and cause diamond to enter the liquid or the gas a ton of energy, which is why diamond has such a high melting point, okay, like 3,550 degrees Celsius. Also tends to be very hard and very rigid, and the reason for that is due to the bonding. These covalent bonds are really strong, they don't give, and so that's why diamond is one of the hardest substances on the planet. Okay, so there you go. That is a picture of diamond. Now we're going to consider a different example, another example of a network solid formed from carbon, which is graphite. If my slide will advance, graphite. Okay. If we look at graphite, graphite is a little bit weird, okay? This is, again, an allotrope of carbon. If we look at the crystalline structure, so this right here is a structure representing graphite and the way that it is held together, okay? If we look at each of the carbons in graphite, these are all sp2 hybridized, which means that the geometry about each of the carbon atoms is going to be trigonal planar. So if we look at this whole piece of graphite, this is really like one big carbon molecule where the carbon atoms are all attached to each other through, here we have a sigma bond formed from the overlap of these sp2 hybrid orbitals right here, and here we have another sigma bond that holds the carbons together, and here we have another sigma bond that holds them together, and another sigma bond that holds these together right here. Okay, that's how the carbon atoms are attached to each other in the plane. So this is really, graphite, if you look at it, really exists as sheets. This whole structure here is flat, okay? And each of these carbon atoms has an unhybridized p orbital, okay? Because they're sp2 hybridized, there's an unhybridized p orbital. This can also be used for bonding, guys, Now, like we said back in Chapter 10, we looked at how the nitrate ion and the benzene ring and everything works with this overlap of these unhybridized p orbitals. These p orbitals all combine to form a delocalized pi system, okay? So we have overlap of all these p orbitals here between all the carbon atoms, and these all form this pi system here, where we have electrons within the pi system that are shared amongst all the carbon atoms. Now, because we have this pi system, okay, where we have delocalized electrons, okay, these electrons can move around. Because the electrons are free to move throughout this pi system, that means that graphite conducts, it conducts electricity. Okay, because the electrons are free to move around. So diamond and graphite have very different properties. The different properties are due to the different ways that they bond and the different hybridization on the carbon atoms. But what do they all have in common? Okay, what do they both have in common? Diamond and graphite both have in common that they're pure carbon, and that also they're attached to the particles, the carbon atoms are attached to each other through covalent bonds. Okay, that is what they have in common, and that is what makes them a network, both of them network solids. Okay, so graphite we just saw is weird because it can conduct electricity. Let's take a look at another picture here of graphite. What I have here on this next slide is a picture of the way that graphite layers. If you were to look at a sample of pure graphite, what you would see is that, like we just saw in the last slide, you have the carbon atoms are all sp2 hybridized. Okay, these are arranged really in a planar arrangement. Each of them is trigonal planar, and so graphite arranges itself in sheets. Within the sheet, okay, if we look within the sheet here, the carbon atoms are attached to each other through covalent bonds. That is very, very, very strong. And so an individual sheet of graphite is very rigid and very strongly held together. But because these are flat, if you look at a sample of graphite that you're just going to pick up out of somewhere, okay, there's layers of these sheets. Okay, so here's one sheet resting on top of another, resting on top of another. If I were to ask you guys, well, what kind of force is acting between the sheets? What holds the sheets together? You can think of this as being one molecule of graphite, really, and here's another gigantic molecule of graphite, and here's another gigantic molecule of graphite, okay? The force that attracts these sheets of graphite is really just going to be dispersion forces, okay? Because each of them is non-polar overall. So a single sheet of graphite is very strongly held together, but the attraction between sheets is very weak. What that allows these sheets of graphite to do is they can slide past each other relatively easily. For this reason, graphite is often used as a lubricant. Okay, if you go buy a very high-end lock at the store, not like my locks, which are cheap from Walmart, but if you get a good lock, the lubricant used in the parts is graphite, because the sheets are able to slide past each other very, very easily. This is also why graphite is useful for pencil lead, because like you could imagine, if what that really requires you to lay down is you're laying down a sheet of carbon on your paper. When you rub your pencil lead across the paper, across the page, you're laying down a sheet of that graphite. You're not breaking the sheet up into separate atoms, you're laying down a sheet, because the attraction between sheets is very, very, very weak. So that's why graphite is useful to write with, is because the attraction between sheets is weak. There we go. So that's graphite. One more network solid we want to look at here really fast, as an example here, are the silicates. Silica is SiO2. Okay. Now, when we talk about organic chemistry, we're going to talk about, organic chemistry is the study of, carbon compounds. Carbon is very important to living things. If we look at inorganic compounds, like minerals and that sort of thing, silicon is really like the carbon of the inorganic world. It participates in a lot of different things. Right here, what we have is a crystalline sample of quartz. And if you look at quartz, that is the structure of silicon dioxide. But if you're going to zoom in on the molecular level again and take a look at how the silicon and oxygen atoms are arranged, it looks like this. There's a crystal lattice like this that is composed of repeating silicon and oxygen atoms. They're all mutually covalently bonded together. Because each of these particles is attached to each other through a covalent bond in this repeating network of silicon and oxygen and silicon and oxygen and silicon and oxygen and silicon and oxygen, the attraction between the particles in this crystal is very, 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 very strong. And so quartz and other silicates and other network solids of similar nature have high melting points and tend to have very rigid structures. And the reason why is because the particles held together by covalent bonds. Okay, let's look at our next class of crystalline solids here, which would be ionic solids. Okay, ionic solids are formed from ions, obviously. So if we look at the individual points in the crystal lattice for an ionic solid, the things that are in the crystal lattice, the individual particles that make up the solid, are ions. Okay, so things that either have a positive or negative charge. So if we look over here, this is a picture of sodium chloride, NaCl. So each of these silver spheres here represents a sodium and a sodium and a sodium, and each of these green spheres is a chloride, chloride, chloride. And what attracts these things to each other is ionic bond, or ionic bonding. Okay, so in other words, the positive things, as we know, are attracted to negative things, and there we go, that is ionic bonding. Because this attraction is very strong, okay, and it takes lots of energy to break the ionic bonds, that means that ionic solids tend to have very, very, very high melting points, okay, because the attraction within the solid is very strong between the particles. Okay, properties of ionic solids, you guys should know. In the solid state, they do not conduct electricity. Okay, they have poor conductivity. Again, the reason why is there are no mobile electrons. Okay, there's no mobile electrons. They can't move around. But when you melt the ionic solid, then that does conduct electricity. So if we were to heat up solid sodium chloride and cause it to become liquid sodium chloride, it would conduct electricity. Or if you dissolved it in water, the aqueous solution of sodium chloride would also conduct electricity. So there we go, guys. That is an ionic solid. Those are the properties of an ionic solid. The last classification that we're going to talk here today, that we're going to introduce, are metallic solids. Okay, metallic solids, okay, are formed from metal atoms, as the name would suggest. So if we look at a metal crystal, the individual particles in that crystal are metal atoms, okay? And these can be either soft or hard, depending on what type of metal it is. They tend to have high melting points because there's very strong attraction, okay? And they tend to be good electrical conductors, okay? Now, let's think about why that is, because we haven't really talked about metallic bonding that much, but you guys did last year. Take a look here at this diagram here on the right. This is a picture of a metal, and let's pretend this is sodium metal. If we think about each of the sodium metal atoms, these have got one valence electron, okay? If we look at a sample of metal atoms, really what happens, because the valence electrons are very loosely held, okay? They're very easily taken away from the metal atoms, and in fact, the electrons, the valence electrons of each metal atom here in the sample of the metal are shared across the entire surface of the metal. So the valence electrons in a metal get shared across the entire surface of the sample. Again, what that means is that you can kind of treat each of the nuclei as being a positively charged cation, and then these are surrounded by a sea. I like to use this phrase, a sea of shared electrons, okay? You know, that are free to flow here throughout the surface of the metal. Now, where the bonding comes in is because if we have this electron right here, well, this positive metal nucleus is attracted to that electron, but this metal nucleus is also attracted to that electron, and it's attracted to that electron, and it's attracted to this electron right here. But this metal atom is attracted to this electron, and it's attracted to that electron, and it's attracted to this electron, and it's attracted to this electron, and all the ones that it can really see. But this metal atom here is attracted to this electron also, and it's attracted to this electron here, and this metal nucleus is attracted to that electron, and attracted to that electron, and this one is attracted to this electron, and to this electron, and to this electron, and this one is attracted to that electron, and to that electron, and to that electron. So we can see that because the electrons are shared between the atoms, each atom is mutually attracted to a variety of electrons, and so that mutual attraction of the positively charged metal nuclei and the shared electrons leads to the metallic bond. That is what metallic bonding is, okay? Now, because the electrons here that are shared, that sea of electrons are loosely held, they're free to flow through the surface of the metal. Because they're free to flow through the surface of the metal, metals conduct electricity, because electricity, you know, as we think about it, really electric current is just the movement of electrons. So because the electrons are free to move, they conduct electricity. Okay, so that is what metallic bonding is. Now, it's a very strong attraction. Okay, that means that it's difficult to break the metallic bonds, and it's difficult to melt a metallic solid because it takes a lot of energy to destroy the bonding. But it also leads to them being malleable and ductile by virtue of the way the bond works. Now, why is that? Well, if these electrons are loosely held, you can see here in this picture that we have, you know, some space between the metal atoms. Okay, there is some empty space in here. So imagine if we hit that with a hammer, okay? So we hit that piece of metal with a hammer. We can cause it to flatten. We can distort the shape of the metal atoms. And because these electrons are free to move, they can just kind of get out of the way, okay? So if we hit this thing with a hammer right here, okay, we could shove this metal atom down this way somewhat, okay? And because the electrons are free to move around, that can happen, okay? If you contrast that with diamond, okay, diamond has a very rigid shape and is very hard because those covalent bonds are, you know, the electrons can't really move around. It has a rigid tetrahedral geometry, and they're not really inclined to move. But because these electrons in the metal are very loosely held, okay, they can move, and that's what leads to metallic solids being malleable, meaning that they are bendy, okay, basically. Okay, that's why, is by virtue of the way that the bonding works, okay? So that is how bonding in a metallic solid works. It is a very strong attraction and leads to having high melting points and good conductivity because the electrons are free to move around, okay? And there we go, guys. That is the different kinds of metals and different kinds of solids, rather, and their properties and the way they're held together. Now, one last thing I want to talk about really fast is the of crystalline solids. There's a whole section in your book devoted to unit cells. Okay, if you guys browse through that, I don't really want you to read all that stuff on unit cells. You don't really have to do that because we're not going to talk about it very much. It's not that it isn't important, but it's not something you have to know for the AP test, and it really kind of gets bogged down in the math. But I just want to kind of show you guys really quickly the idea behind the structure of a crystalline solid. So let's take it. If we consider a crystal as we know it, okay? A crystal is a regular arrangement of things in space. So here's just a picture that represents a crystal lattice. So here we have a crystal lattice. We have a regular arrangement of these points here in space. Now, the difference between the different classes of crystalline solids we've talked about so far is they all have a basic, you know, structure that looks something like this, where you have a repeating arrangement of particles in space. The only difference between a molecular solid and an ionic solid and a metallic solid and a whatever else the other, I'm losing my mind here, a network solid is, the only difference between the three of those is what are these points, okay? The identity of these points, whether each of these particles here, the lattice points, are molecules or atoms or ions. That's really what determines what type of a crystalline solid it is. Okay, but all crystalline solids have a regular structure. Okay, it's going to be that's what a crystalline structure is. Okay, now you can think about this structure here as a whole. Okay, as being a repeating pattern. Okay, of a smallest unit. Okay, so if we take a look, we can see that if we take this three-dimensional shape right here, this cell, okay, and we were to replicate it and move it over here and 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 over here, okay, really this crystal, the entire structure is kind of like repeating units of this cell right here, okay? The smallest unit of a crystal that has the same structure as the crystal and same arrangement of particles is called a unit cell, okay? And there's different arrangements, different types of unit cells, okay? There's a whole bunch of different kinds. The three basic ones are called a simple, or sometimes called a primitive cubic, or also called a simple cubic unit cell, okay, where the smallest unit of the crystal looks like this. You have a cube shape, and at each of the corners of the cube, you have one of the particles, okay? Now, these particles can be either molecules, okay? If it's a molecular solid, it can be ions if it's an ionic solid, or it can be atoms if it is a metal, or if it is a covalent network solid, okay? Now, if you have something where you have a simple cubic unit cell, okay, the crystal as a whole is going to be basically just repeating, it's going to be a bunch of these it's going to be a bunch of these simplest structures, a bunch of these cubic unit cells that are basically stacked on top of each other, and that's built up to make the crystal. So it's a repeating pattern of that unit cell. Okay, you can have other types of unit cells also. This one down here is called a face-centered cubic. Okay, it's kind of like, just like this one right here, but you've got another atom here sitting on the face of the faces of the unit cell. That's why it's called a face-centered cubic, because on this face of the cube, I've got an atom, or an ion, or a molecule. You can also have something called a body-centered cubic, where you have one of the particles here in the middle of the unit cell. So these are just examples of unit cells. All I want you really to know about these is that if we consider a crystal, if we look at a crystalline solid as a whole, the entire three-dimensional structure is basically a bunch of individual unit cells of whatever type that crystalline solid uses. Okay, so you're never going to have these types mixed and matched. It's always going to crystallize according to one of these three different modes. But the crystal as a whole is built up as repeating units of that simplest unit cell. Okay, that's all I really want you guys to know about unit cells. Just keep in mind the idea that a crystalline solid is a repeating arrangement of the same pattern of stuff in three-dimensional space. Okay, guys, that is the end, our notes for today. So I want you guys to read the section on solids in your book, but you can skip the whole stuff about unit cells. That's not going to be that important to you. So here's your assignment that goes along with this podcast. This is going to be Chapter 13, Assignment number 3, okay, and you're going to do problems number, okay, let me find my paper really fast. All right, for tonight, guys, do problems 42, 43, 55, and then 60 to 65. Now, I am also going to post on the website some old AP questions you guys should also print off and do. These have to do with phase diagrams, kind of review from before, and then once we get back to school, I'm going to have a review assignment for you guys to do as well. Thank you very much, guys, for all your hard work. If you've gotten this far, you're doing very well, and so I truly appreciate the hard work you're doing here over your break, and I assure you that it is going to pay off. So guys, please enjoy the rest of your break, and I will see you when you get back to school. And remember, guys, find questions that you would like to see answered, things that you have questions about, and I will address those here in an end of the week type podcast. So have a good time until then, guys. See you when we get back to school. Goodbye.